G'day gents, this is Kai for Taught Through Gaming. Today we will look at what the free body diagram is, what the parts of it are, and how to apply it to a few situations in War Thunder. The free body diagram is a simplification of a system to analyze the forces acting on it. Our system can be anything from a rock on the beach to a beautiful Mirage 2000. Every system has a center of mass, which, simply put, is the point of balance on the system. If a spike were put at that point, the entire system would be perfectly balanced. It wouldn't tip over on any axis. In a free body diagram, we assume that all forces acting on the system are acting perfectly through this center of mass. This doesn't work in some situation, but ends up working pretty well for general analyses. So, let's look at the Spitfire Mark IIB in level flight. If we take this whole plane to be the system that we are analyzing, then we can say that there are four forces acting on it. Those are lift, weight, thrust, and drag. We represent the forces with arrows pointing in different directions, representing the directions that the force is acting in. While you can draw the arrows pointing towards the center of mass rather than away from it, it's fairly standard to see arrows pointing away from the center of mass. So, that's basically what a free body diagram is. Let's look at a different system. Instead of a flying aircraft, let's look at this ARL-44. In this case, we won't have the same four forces we had in the previous example. In fact, we'll only have two forces acting on the tank. We still have the weight of the tank, but the second force will not be a lifting force since the tank doesn't have wings. Instead, a normal force pointing upwards on the tank from the ground will keep it from sinking into the ground. Wait, hold on. Rewind that? At this specific point in time, we actually have four forces acting on the tank, but one of these forces is a bit special. It's called an impulse. Impulses are forces that only act for a specific amount of time on the system. In our case, the shell being fired produces an impulse both on the shell and on the tank. However, we have a problem. Our system isn't balanced with the forces that we just have on the screen right now. If these were the only forces acting on our system, our tank should be sliding backwards, but that's not happening. So, some other force needs to be acting on the tank, and that force is friction. Since the tank wants to move to the right, friction is acting to the left and counteracting this desire to move. This means all of our forces are balanced. When all the forces on a system are balanced, we say that this system is balanced. In the case of this ARL-44, our system is not only balanced, but also at rest. Oh, well, better luck next game. In any case, if this ARL-44 was at rest, then was the Spitfire from before also at rest? In short, the answer is no. The system is in fact balanced, but the velocity of our system is not zero, so our system is not at rest. Systems can be unbalanced though. Look at what the Spitfire is doing right now. It's pushed up the throttle. This is causing the velocity to increase. In our case, our thrust force is now greater than our drag force. What does this mean? According to Newton's second law, the acceleration of an object depends on the mass and the amount of force applied. So when our forces are unbalanced, our system is accelerating, which is why the airspeed increases. Those are all the basics of free body diagrams. Thank you for your attention. I hope you learned something.